Okay, so this will be the last video for 10.3. What we're basically going to do is put it all together. So again, keep in mind we have our multiplication rule, right? So if I have the same index, I can put it all underneath one radical and multiply my radicands. Or when we have a power that matches the index, basically they cancel each other out and we're just left with a. So we're going to put that all together here in this example. So for starters, we have the square root of 12 times the square root of 3. So initially not much we can do, but we can multiply. So this becomes the square root, I'm going to cut to the chase, of 36. Now that's really nice, right? Because what is the square root of 36? It's 6. So that one was very easy. After multiplying together, the simplification just fell through. So I wish they could all be that easy, but they're not, so we'll just keep on working. All right, so the next one, we have the square root of 15 times the square root of 5. Again, neither radical is very nice, but if we use our multiplication rule, 15 times 5 is 75. So we're basically looking at the square root of 75. So how do we simplify that? Do we have an opportunity here to use that guy? Well, if we come over here and start factoring, we already know that, and we know that. So this is 5 squared times 3. So my power here matches the index, so there's a 5 that comes out, and unfortunately, there's a 3 that stays in. So I'm first putting it together by multiplying, and then I have an opportunity to refactor, re-break it up, and simplify. So that's pretty much what's happening. It's kind of like we're going one way and reversing ourselves going the other way as we simplify. Next round we have a cube times a cube, x squared, x squared. So that becomes the cubed root of x to the 4th. All right. If I'm using my shortcut, I'm thinking that this is x to the 4 thirds, which is 1 1/3. So we get x and the cubed root of x. If you don't like that, x to the 4th breaks up into x cubed times x, and so you can basically see there's a power that matches the index, so an x comes out and essentially an x stays in. So whatever route you like. So I'm kind of using fractional exponents, where I'm just basically breaking things up into powers that are useful, right, that match the index. So whatever works. Hopefully by this time you're kind of getting a feel for what you like best. Next round, we have a cubed root times another cubed root, so that's good news. We can put that all underneath one radical. 9 times 6 would be 54. Right, that's a cubed root, by the way. X times x to the 4th, well, that's x to the 5th. And y squared times y to the 5th is y to the 7th. So we have some simplification issues because I can obviously see some powers are larger than my index. So we got to break this down. 54, fortunately, we already have seen that. That's 27 times 2. This is x to the 3rd times x squared. This is y to the 3rd times y. And so we're taking the cube root of each piece. So we know that the cube root of 27 is a 3. There's an x that's going to come out, and a y and a y. So we have y squared. What gets left behind is everything else. So a 2 stays in the radical, an x squared stays in the radical, and a y stays in the radical. So I'm thinking, you know, I have a feeling, again, every class kind of likes that version rather than the fractional exponent. So I'm just going to leave it at that. So that's a pretty simple version of that. So again, we multiplied first and then saw an opportunity to simplify, and we broke it up again. Next example, we have a couple of 4th roots. So I'm going to keep that 4th root. We have a y squared and a y to the 8th. So adding my exponents, that becomes y to the 10th. We have a y plus 2 to the 3rd and a y plus 2, and that's a 7 right there, believe it or not. So we have a y plus 2 to the 10th. Okay, so obviously my powers are larger than the index, and so basically what we have is y to the 4th, and y squared. And then over here we have y plus 2 to the 4th, another y plus 2 to the 4th, and a y plus 2 squared. And we're taking the 4th root of all that. So lots of opportunities, right? Again, 4 and 4 and 2 would add up to 10. So that's why I'm doing that. There's a 4, there's a 4, there's a 4, and there's a 4. So it looks like we get a y squared coming out, a y plus 2 squared coming out, And then the fourth root, it looks like we have a y squared and a y plus 2 squared. Okay, so it looks like we're pretty much done here. I'm going to put a little asterisk on this as we learn a little bit more. It turns out that there's more we can do, but for the rule we're learning and for where we're at, that's good, right? My power and my index, or excuse me, my power and size lower than my index. We've simplified as much as possible. So one last one to talk about. Let's end this whole thing by looking again at the cubed root of x times the cubed root, or excuse me, the fourth root of x. Again, fight the urge to say, oh, this is so easy, I'm just going to put it together. Because look real carefully, right? This is tough because the indices are not the same. So we can't use any of our multiplication rules to simplify that. So what we need to do, right, is we actually need to convert this to their fractional exponent form and use that. So this becomes x to the 1/3 plus 1/4. Adding fractions, we find a common denominator, so 4 over 4 and 3 over 3, that's 4 over 12 and 3 over 12. So we end up with x to the 7/12. Finishing off with radical, there would be my final answer. So be careful. It's a great rule, but the only time I can use it is if my indices are the same. If they're not, you need to go back into 10.1, or excuse me, 10.2 and use that information there. Otherwise, you got it. Match the power, match the index, you simplify. All right, so that should wrap up 10.3. Give me an email if you need help. Jump on Canvas, whatever it takes. There's lots of help out there. Talk to you guys later in the next section.